Here's a quick video on how to use LTspice to help you study for an exam. Even if the exam is closed book, closed note, and closed artificial intelligence and closed LTspice, it's still great to check your work, and I'll tell you how. So it's not enough just to do the regular homework. And let's say this problem was assigned and you have the solution and you're trying to study, right? Now, maybe the professor has a lot of worked out examples you can go from, or they're using a book that has a lot of worked out examples. But it's not always the case that this happens. In fact, the farther up you go, the least likely there will be to a lot of worked out examples. And so you will have to create your own worked out examples. So this would be a classic RC low pass filter. Many ways to solve this. But you get pretty much 1 minus e to the minus t divided by RC for times greater than or equal to 0. You're saying, well, let me just make up a circuit that will test my knowledge. So you're going to take these resistors and make 2 of them, and now you have 1, 2, and 3 nodes. You can go through this, right, to try to solve this. And why don't we do it? So no matter what, this is a first order circuit. There's one capacitor or a bunch of series and parallel capacitors that can be reduced into one, and we have 2 resistors, right? So that'll be a first order circuit. The solution to this is going to be e to the minus t tau, regardless. One easy way of looking at tau is to see, well, here's the voltage source. It has an impedance of 0. And we have 2 resistances and a capacitance. So just kind of going around the loop. And by the way, this is a really quick way, but not necessarily generalizable way to do these problems. But we're going to get 2RC for our tau. All right, now then the next trick is over time, we have a step at 0. We go from 0 to 1. And then we have, 5 tau is where it should be. Well, for times less than 0, this voltage is 0. So if this is 0, no potential, and it's 0, everything is 0, there's no current, nothing will flow. So there can't be any voltage drops. Let's just do that in blue. All right. Now and we're talking about node 2 here, right? Because node 3 is really just this problem here, except you just have to do 2R, combine these. But we want node 2. So at t equals 0, that's when the step occurs. That step can cause what you might just call a high frequency signal, or even infinity. If I look at the impedance of a capacitor at 1 over j omega c, infinity frequency makes this capacitor short to 0. Right, so that would be shorted. And so even though I'm at 1 volt here, right at the step, this is shorted, and so I have current flowing, and I get a voltage divider, right? And it will actually kind of, let's just call it V in R divided by R. If they're the same, it'll just be 1/2, right? Then let's look at a long time after the step, or 5 tau, right? That looks DC. And so DC the impedance would be 1 over J0 C goes to infinity. This is an open circuit. No current can flow. Therefore, there can be no voltage drop. And so node 2 goes to our 1 volt. It ends up here. All right. Now, how does it get there? Again, we have to have that exponential in there. It's a first order RC circuit. The only thing that solves that is a decaying exponential. So we can just kind of draw that in, right? So at time equals 0, I'm just going to call it 0.5, saying that's 1 volt. The resistances are equal. All right, so it just goes to 0.5. And then at some point, it's got to go to 1, right? So how do I get that? I have to add 0.5 minus e to the minus t to RC for times greater than 0, right? Nope, that's not quite right, because that will be 1. No, wait, at time equals 0, I want this to be 0. So this would go to e to the 0 is 1. 0.5 minus 0.5 would be 0. I'd be left with the 0.5. All right. And forgive me, I'm a bit of a rush today. But the thing is you might make a mistake in doing a problem like that. And maybe I have. All right. Where does LTspice come into it? Well, here is, let's say, the original problem. I'll just manipulate it a bit. And to make it easier on myself, I'm going to split it in two, because I've already set it up for... So 5 kilo ohms, 0.1, I should get a time constant of 1 millisecond. And this is set up for actually to mimic the simulation of the M2K from Analog Devices. So let's run it. And what do we see? We see this sharp increase to 0.5, then an exponential increase to 1. I'm actually running this for 10 tau for other reasons I won't get into. But if we make the period 10 and t on for 5, it'll be on for 5 tau. And you can see that it gets almost to where it's going within 5 tau. But then when it turns off, we get this immediate change in level, and then it decays back down to 0. Which now we're somewhat going off script here. I haven't practiced it, but I can add a behavioral source, call it check, and I can check the first part. It'll be a little bit harder to check the decay. So I have my DC plus 0.5 times 1 minus e exponent minus time. You can't use t. You got to use minus time. Divided by 10k divided by 0.1 u. Oop. Now, Spice only runs from time t onward, so I don't really have to put a step function or say anything like for t equal greater to 0. And I need one more parenthesis. All right. I'm just going to move this where I can see it. And rerun. Hopefully I don't have a... Just pressing Control. That way I can select more than one. And yeah, it matches. Now, does it come back down? No, because I haven't set it up for a repeating signal. So it's just really the step response. So I've checked my work, right? Now I could have made a mistake in the schematic, right? And done 10K here and 10K. And you'd see that the tau was different, right? So you can make mistakes. It could be here, it could be in your logic, whatever. But in general, if there's a difference, when you find out the reason for the difference, 9 times out of 10, you get the correct answer as well. Hopefully, you can generalize that to, any class from even physics, your electromagnetic series, to your introduction to circuits, to your advanced circuits. So you can generate your own problems and answer it. And let's say you come up, there's a mistake you can't find. Go to your professor during office hours and, just say, I was studying and making problems on my own and I ran into this problem. I can't seem to solve it. Can you help me out? They will love it. Heck, I'd love it if you did it and came to see me. Take care.